I'm Andre. I'll be your session chair for this session. So for the speakers, I will give you like a short warning, 2 minutes and 1 minute before you're talking with this and this. And without further ado, the first paper we have is Robust and Sample Optimal Algorithms for PSD Low Rank Approximation by Ainesh, Nadia, and David Woodruff. And Ainesh will give the talk.
All right, thanks, Andre. All right, so let's get started. I'll begin by defining the low-rank approximation problem. Here you're given as input an n by n matrix A and an integer k. And pictorially, the goal is to take this matrix A and factorize it into U times V, such that the inner dimension of U times V is k. And then we return this factorization, and hopefully it is close to the original matrix to begin with. A bit more formally, we want the product of U times V to be close to A in squared Frobenius norm, where recall the square Frobenius norm is just the sum of the squares of the entries of the matrix. And since we constrain the inner dimension of U times V to be U and V to be k, the resulting product has rank at most k. Okay, so why consider the low rank approximation problem? It helps you compute a compressed representation of the input matrix. You can reduce the number of parameters that you have to carry around. And it's also often used to detect structure in real-world data. And it's used as a subroutine for clustering, statistical modeling, distribution learning, etc. So this problem is really well understood. And even though the objective that we're trying to optimize is non-convex, it admits a really nice closed form solution. This closed form solution is given by the truncated singular value decomposition, where the singular value decomposition is the factorization of the matrix into a matrix with orthonormal columns, orthonormal rows, and a diagonal matrix which has the singular values on the diagonal. Okay, to get a rank k matrix out of this, we truncate all but the top k singular values. And when we multiply them together, we get a rank k matrix. And it's been known since the 30s that this is optimal. Okay, but we are interested in randomized algorithms for this problem since we don't want to compute the full singular value decomposition and truncate it. And in a seminal work by Clarkson and Woodruff in 2013, they show how to compute a rank A matrix B that is close to the input matrix A in squared Frobenius norm. In particular, it is at most 1 plus epsilon times the Frobenius norm of A minus AK, where AK was the truncated SED. And this is the optimal cost. And crucially, the running time of this algorithm is linear in the number of non-zero entries in A. So it scales proportional to the sparsity of the matrix, linearly in the sparsity of the matrix. Okay, and it's also not too hard to see that reading the entire input is necessary. Consider the following toy example. We have a matrix which is all ones, except one entry is really large and it is randomly placed somewhere in the matrix. The resulting matrix has rank 2. And in order to get a low rank approximation to this matrix, any non-trivial low rank approximation, we have to find where this really large entry lies. Otherwise, you'll pay error proportional to it. Okay, so the complexity of this problem is well understood when you have to read the whole matrix and there's a matching upper bound. Okay, so for the purposes of this talk, we will focus on a positive semi-definite low-rank approximation. Here, you're promised that the input, instead of being an arbitrary matrix, is a PST matrix. So let's recall what a PST matrix is. Now, there are many equivalent definitions, including all the eigenvalues of A being non-negative. A can be written as an inner product matrix for some QQ transpose, and all quadratic forms of this matrix are non-negative. So these are equivalent definitions. We can use any one of them. To summarize, the problem is again as follows. We are given a matrix A, which is PST, and we want to compute a rank K approximation to it. And the notion of approximation we want is 1 plus epsilon relative error. Okay, so why would we want to study such a problem? Well, consider the following example that might appear in practice. So we are given an n by d data matrix D. And consider the matrix A to be D transpose D. This is the empirical covariance matrix of your data set. And several tasks involve projecting onto the top K subspace of such a matrix A. And also, this matrix, the covariance matrix could be really large and you don't want to carry it around everywhere. So you can instead store the low rank approximation, which is a compressed representation of the covariance. Okay, with that motivation in mind, the main question that we want to understand is whether a low-rank approximation for a PST matrix requires reading the entire input. So we saw for general matrices, it's necessary that we should read all the entries, all the non-zero entries in the matrix. Does the same continue to hold if you're promised that your input is PST? So this question was first addressed in this beautiful work by Moscow and Woodruff. And what they show is that you actually do not need to read most of the matrix. This is quite surprising. What they show is that you can get a linear dependence on the number of entries that you have to read in the matrix. So linear dependence on the input dimension, and a polynomial dependence on the target rank k and the desired accuracy epsilon. So the exact terms are not important now. I'll get back to them in a bit. So a cartoon of how their algorithm works is that you're given a matrix, you're promised that this matrix is PST. They query a very few entries in the matrix, they don't read most of it, and show that this is sufficient to compute a low-rank approximation to the input itself. Okay, in addition to this algorithm, they also provide a lower bound on the query complexity, and they show that a linear dependence on n, k, and epsilon is necessary. So in other words, if any algorithm reads any less entries of the matrix than linear in n, k, and epsilon, then it's information theoretically impossible to output a low-rank approximation. If that summary was a bit too fast, here's a picture to summarize the results that were known before our work. So on the x-axis here, we have the query complexity. And above this threshold of nk over epsilon to the 2.5, we have fast algorithms. Below this threshold of nk over epsilon, and the problem is information theoretically impossible. And there's a gap here, and we don't know what the right complexity of the problem is. Further, there's like a foreseeable obstacle to resolving the complexity of this problem, which involves a quadratic dependence on 1 over epsilon. And intuitively, this quadratic dependence is coming from the concentration or measure kind of arguments that a lot of algorithms make in this area. And you might have seen something similar for, let's say, the Johnson-Linden-Strauss transform. Okay, so our main result is to resolve the sample complexity of this problem. We show a linear in n, k, and epsilon number of queries suffice. Further, our running time is also linear in n, k, and epsilon if the matrix multiplication constant is 2. So that's an interesting connection. And let me redraw the picture now to show, to include our results in it. So on the x-axis, we again have the query complexity, and on the y-axis, we have the running time. And above this threshold of nk over epsilon, we have a nearly linear time algorithm. And below this threshold, the problem is impossible. So there's a really sharp phase transition here at nk over epsilon. And I really like this because it shows that there is no computational versus statistical trade-off for this problem. Okay, so I don't have time to tell you how our algorithm works in any detail. I do that in the longer version of this talk. But what I want to talk about is the standalone problem that we encounter in this work, and we show how to solve. And this problem is a twist on a problem that you might have seen before. So here we have a regression objective. So we are given two matrices y and z, and we want to minimize z times x minus y. And typically, for regression, the norm that you want to minimize between these matrices is the Frobenius norm. But instead, here we are interested in minimizing the operator or spectral norm, and hence the name spectral regression. So this is a problem that shows up in our work, and we want to understand how to solve this. In full generality, but for our application, we also want to solve this problem in sublinear queries to the matrix Y. So we want to make sure that we don't read all the entries in this matrix. Okay, so we show how to obtain a 1 plus epsilon approximation to this problem by querying a very few number of entries in the matrix, in fact, not reading most of it. So if you think of Y to be an n times n matrix, we only read a linear in n, d, and epsilon number of entries, where you should think of d to be much smaller than m. We also characterize the approximate optima of this regression problem. Okay, so a few applications of the techniques that we develop in this work. So we can extend our approach to outputting a low rank approximation, which itself is PSD. So in the original problem, we had no constraint over the low rank matrix that we end up outputting, but we can also accommodate this additional constraint that the output itself is a PSD matrix, and this is important in some applications. And we obtain optimal sample complexity and running time for this problem and improve prior work by polynomial factors. Another problem that might a priori seem unrelated is that of low-rank approximation for negative type matrices. So a negative type matrix is a distance matrix where the distance metric that we are considering is the squared Euclidean norm equipped with triangle inequality. So this is a very general metric. It captures well-studied metrics like L1, L2, etc. And we show that we obtain optimal sample complexity and running time for such problems as well. And it improves on prior work by getting rid of bi-criteria approximation that appeared in them. And finally, we introduce a new model of robust low-rank approximation, which we study in the context of PSD matrices. And it's robust in the following way. So instead of being given a truly PSD matrix, you're given a perturbation of a PSD matrix, and you want to see how well you can do. Okay. So I'll conclude with some open questions and directions for future work. So recently, this line of work has become really popular, studying linear algebra problems for a structured family of matrices, and some families that have been considered are PSD matrices, distance matrices, Van de Moon and Henkel matrices, and Toeplitz matrices. And there's so much to do here. You can pick your favorite linear algebra problem and ask what happens when you consider these special families. Another line of work that I really like is estimating matrix norms for structured families, either in input sparsity time or in sublinear time if you assume the matrix is bounded. And there's been some really interesting work on like spectral unshadowed norm estimation. And finally, a somewhat tangential direction to this is to consider linear algebra problems in the framework of property testing. So we introduced one such problem, which is testing PSD-ness. And if this sounds interesting to you, check out Raj's talk on Thursday, also at FOCS. And finally, while we are designing all these algorithms, it's good to take a step back and ask, how robust are the algorithms that we design to the assumptions that we're making? So, like how robust is this algorithm to the assumption that the matrix is PSD? And do our algorithms decay gracefully as these assumptions stop to hold? Okay, I will stop here and take questions.
Thanks, Anish. Questions for Anish, you can either put them in the chat and I can read them off, or you can unmute and ask, or you can put them in the Slack. I'm monitoring all.
There's a question, is the output matrix BPSD? It doesn't need to be, but okay.
You can get that. That was like right as you were like going through that slide, actually.
Can you quickly say what the sampling algorithm is?
Yeah, it's not a one-state sampling algorithm. We describe it in the longer version of the talk, but at a very high level, you begin with sampling proportional to these things that are called ridge leverage scores. So you sample some rows and you sample some columns, you get a thing which is known as an approximate projection cost preserving sketch, and then you have to do a lot of work on top of this.
Perhaps this has like a simple, I guess, like a quick one-sentence answer. Do you think this reduction to this regression problem that you reduced it to could also have applications for other problems, or is it kind of very strongly tailored to your problem?
We believe that this regression problem should have other applications standalone. Yeah. Thanks.
Cool. Great, thanks, Anish. So next up, we have near optimal linear algebra in the online and sliding window models by Vladimir Petros, Cameron, the Muskos, Jalaj, David Woodruff, and Samson Joe. And I don't know who's giving the talk. Maybe whoever's giving the talk. Yeah, okay. If you could screen share, that'd be great.
Okay, can you see my screen?
Yes, you're visible and audible.
Okay, yeah, so I'm giving a talk on near-optimal linear algebra in the online and sliding window models. This is work by, and I can't scroll through, 1 second. There you go. Okay, this is work by Vladimir Braverman, Petros Stranaeus, Cameron Musko, Chris Musko, Jalaj Apaje, David Woodruff, and I'm Samson So. So let's start by breaking down the titles, in particular the models in the title. To understand the sliding window model, we first need to review the streaming model, in which elements of some underlying data set S arrive sequentially. And the goal is to evaluate or approximate some predetermined function using space sublinear in the size n of the input. In the sliding window model, only the n most recent updates form the underlying data set. For example, if we have a stream of bits and we only care about the 8 most recent bits, then when we have 11 bits, the sliding window will only capture the bits in the box that is shown on this slide. So the sliding window model emphasizes recent interactions, and thus it's a bit more appropriate for applications in which time-sensitive issues matter more. We'll consider the row arrival model, in which we have an underlying matrix A, which has dimensions n by d, and the rows of the matrix arrive 1 by 1. So until, in this case, 6 rows arrive, all the underlying rows form the data set. But when we get the 7th row and the 8th row, then we only care about the 6 most recent rows. So as I already mentioned, the sliding window model emphasizes efficiency and recency. And we already use linear algebra in strategies that are based on optimizing and predicting future patterns based on past data. But we don't want to use outdated information, so it seems like a natural thing to consider linear algebra in the sliding window model. We give the first sliding window algorithms for spectral sparsification, low-rank approximation, and L1 subspace embeddings. These algorithms are all time efficient, and furthermore, for the first 2 algorithms, they're all space optimal up to lower order. The second model we discuss is the online model. And here we still have a data stream. So we still have some set S, which arrives sequentially. And the goal is to evaluate or approximate the function on S using space that's sublinear. But here, in each time, we have to make some decisions that are irrevocable. So we see a row, and we choose to either discard it or keep it forever. This is more appropriate for applications where we need to make some decision and send our decisions downstream for some further processing. We obtain the first algorithms for low-rank approximation, row subset selection, and L1 subspace embeddings in the online model. And we also get an algorithm for online PCA. Our algorithms are all space optimal, and they're also time efficient. So to discuss our actual algorithms, let's first have a problem in mind, so we have some kind of working example. The problem we'll talk about is spectral sparsification. We're given an accuracy parameter epsilon and an input matrix A that has dimensions n by d. The goal is to find a matrix M with dimensions little m by d, where little m is much smaller than n. This matrix M has to have the property that for any input vector x, the 2 norm of mx is roughly the 2 norm of ax. It can be shown that this is equivalent to requiring that M transpose M is roughly spectrally equivalent to A transpose A. It can also be shown that this, when A transpose A is graph Laplacian, that this matrix M approximates all cuts of a graph. It can also be shown that A can be massaged slightly, so that when the input is A concatenated with B, then we can recover the vector x that approximately minimizes the 2 norm of ax minus b. And this gives the least squares optimization to the linear regression problem. Now that we have a working problem in mind, let's discuss some of the challenges we have in the sliding window model. A natural approach would be to use the smooth histogram framework by Braverman and Ostrovsky. This gives a number of algorithms for the sliding window model, but it requires that the input and the desired function are smooth. And this is a property of functions that are scalar valued. But here we deal with matrix values functions, so it's not immediately obvious how to extend this idea to our setting. Another approach would be to use sketching techniques for subspace embeddings. For these techniques, we have a sketch matrix P, which is short and wide. And throughout the stream, instead of maintaining A, we maintain P times A, which is much more efficient. But this is problematic in the sliding window model because rows implicitly expire. So when we get more rows of A, we can still maintain P times A, but when the rows expire, we have to undo the effects of P times the row that expired, but this is implicit, so we don't actually know the row that expired. So this also seems problematic for the sliding window model. Another approach is to use sampling techniques for data streams, which is to see every row and then sample these rows based on some quantity of importance for whatever definition of importance is relevant to the problem. This also seems problematic because more recent rows seem to be more important, which is not a property in data streams. For example, let's suppose that we see these first 3 rows. Let's suppose we sample the first row, and suppose we sample the second row. Now the third row looks like a carbon copy of the second row, but it's just much smaller in norm. So intuitively, it seems like the third row should be much less important than the second row. And let's assume for now that we choose not to sample the third row. Now suppose that the data stream continues, and at some point, the underlying matrix A in this box is just the third row followed by a number of rows that are all zeros. Well, if we didn't sample the third row, that's the only non-zero row. So it doesn't seem like we can get a good approximation of A without storing the third row. So this also implies that we should always store the most recent row. And thus we need a new quantity that accounts for both how important a row is for some measure of importance, and also how recent a row is. So this leads to our algorithmic template. And our algorithm is as follows. At each time, we maintain a number of rows from A that we've sampled. Then we see a new row, and we repeatedly downsample each stored row AI based on a probability distribution tau I that we call the reverse online score. And this is a quantity that accounts for both the importance and the recency of a row with respect to some desired function. We prove correctness by using a martingale argument to show invariant that each sampled matrix is a good approximation to the underlying matrix, so that each row AI is sampled with probability proportional to the final reverse online score. So this is correctness, but we still need to analyze the space complexity. And since we sample each row with probability proportional to the final reverse online score, then we have to bound the sum of the reverse online scores. This leads to a number of structural results that we show. For spectral approximation, it turns out that Cohen, Musko, and Pechke already showed that the sum of the reverse online leverage scores is roughly d log kappa, where kappa is informally a quantity that represents the condition number of the matrix. For logic approximation, we instead consider the reverse online ridge leverage scores, whose sum we show to be k log kappa. For L1 subspace embeddings, we show that the sum of the reverse online L1 sensitivities and the online Lewis weights, which we define, are d log n log kappa. And combined with the results on the previous slide, these quantities show that our algorithms are correct and have a certain space bound for each of these algorithms in the sliding window model. So this gives our results in the sliding window model. Now it turns out that the sum of the reverse online scores is actually equal to the sum of the online scores. And thus we can use our same algorithm, our same approach, and essentially get online algorithms for free. Moreover, it turns out that our algorithms admit what's called an online core set, which is an algorithm whose output can be used to approximate all prefixes of a stream. We show that these online core sets translate to deterministic sliding window algorithms, and thus we use our online algorithms to get sliding window algorithms that are deterministic for spectral sparsification, low-rank approximation, and L1 subspace embeddings. And these are all space optimal up to lower order terms. Note that this technique, in fact, improves upon the L1 subspace embedding algorithm for randomized algorithms that are based on these sampling scores that we discussed earlier. Okay, so that concludes my talk. for more questions, I'll be here at the poster session, and please take a look at our longer talk online. Thanks.
Great, thanks, Samson. Questions about Samson?
Samson, I have a question. So
yeah,
the model, the sliding window model, when A is the vertex edge incidence matrix of a graph, this can be thought of as an edge addition followed by an edge deletion. Am I right?
When A is the edge incident matrix of a graph.
Vertex edge. So for spectral sparsification, one of the examples you gave was to think of A as the vertex edge incidence matrix, right?
That's right. Yeah.
So in that viewpoint, the sliding window model can be viewed as an edge addition followed by edge deletion. Am I right?
That's right, but it's a bit peculiar in this case because the rows kind of expire. So what would have represented like the second vertex would now represent the first vertex. So it's a bit strange to consider this exact problem in the sliding window model, but like in—
Sorry, I thought the rows correspond to edges.
Oh, I see.
So what expires is an edge. So it's an edge deletion followed by an edge addition. A new row arrives means a new edge arrives.
Yeah, that's right. But then it's not quite an edge deletion. It's like, you just care about the endmost, a certain number of recent edges.
Right, but the sliding window model can be thought of as, okay, the recency matters, the ordering of the edges matter.
Yeah. But yeah, otherwise, yeah, you're right. Yeah.
Okay, thank you.
Other questions? So maybe quick question, though I'm an outsider, so forgive me if it's a little bit ill-informed. So I guess like you have like several results, right? Like so it's you have like basically multiple kind of results for the sliding window setting. So is there like something common on the level of techniques, or they're all kind of sort of different, but like per result kind of basis?
Yeah. So we give a framework for randomized algorithms, which is this template that I discussed earlier. So at each point, you want to sample these rows with some quantity tau I. And that's like, if we black box the tau I, then all of these results fall under this framework. Now we have to give structural results to actually bound each sum of the tau I's to get the space complexity of each of these algorithms. But yeah, so we have a framework for the randomized sliding window algorithms. And using this online course set that's actually on the slide, we also have a framework for deterministic sliding window algorithms. So basically for deterministic algorithms, if we have an online course set, then that immediately translates to a deterministic sliding window algorithm. So this kind of shows a connection between the sliding window model and the online model. We also show, using our structural results, that we can get equivalent algorithms in the online model. So that, the equivalence kind of goes both directions. If that makes sense.
Yes, definitely.
Okay.
Cool. Thank you. So next up, we have pseudospectral shattering, the sign function, and diagonalization in nearly matrix multiplication time by Jess Banks, Jorge Vargas, Archid Kulkarni, and Nikhil Srivastava. And I suspect Jess is giving the talk. I think I saw her in the. Oh no, Jorge.
Yeah, I'm giving the talk.
Go for it. I can see your screen, and you're good to go whenever.
Okay. Yeah, let me just go to full screen. Okay, thanks. So let me just begin by formally defining the approximate diagonalization problem. So this can be phrased, so this is an algorithmic problem, and it can be phrased as follows. So let A be an n by n matrix, and let delta be an error parameter. Then find V0 and D0 with D0 diagonal, such that this inequality holds. So in the context of numerical analysis, this is a backward error formulation. And if you think about what this is asking you to do, is to exactly diagonalize a matrix that's near to A. And how near, it's controlled by this error parameter delta. So this is not an easy problem. And of course, it has the common complication to all numerical analysis problems that you can't do operations exactly in a computer. But particular to this problem, so this manifests in the fact that non-Hermitian matrices have very unstable eigenvalues and eigenvectors. So it's hard to get algorithms that give an accurate output. So surprisingly, very few is known about this problem. So the Hermitian case is much easier because so Hermitian matrices have much more stable eigenvectors and eigenvalues. So that was solved a while ago. And in '94, Psi proved that this can be solved in polynomial time. The downside of Psi's result is that the number of bits of precision that is required for his algorithm is polynomial in n. Whereas, for example, here you have a logarithmic dependence in n, and this already makes the algorithm impractical. Moreover, the exponent here is not great. It was something like n to the 12th. So actually in '97, Demel in one of his books wrote this, the problem of devising an algorithm for a non-Hermitian eigenproblem that is numerically stable and globally and quickly convergent remains open, right? So, okay, one can argue that this problem was solved in 2015 by Armentano et al. So they showed that using n to the 10 over delta square number of bit operations and polylog n over delta bits of precision, this problem can be solved. So maybe just to point out that here there's a 1 over delta square dependence, that's not great, right? So these ones have log of 1 over delta, and that's kind of like what one wants. And as a side note, MATLAB, for example, the I command runs in n cube in practice. So that's kind of like what it's observed. But what you know that there's no known guarantees. And actually, I mean, there's no guarantees because it can fail. And see how there was still a gap between what can be proven and kind of like what's observed. Okay, so let me tell you our main result. So we showed that there's a randomized algorithm which solves this problem in nearly matrix multiplication time. And just to be more concrete about what I mean by matrix multiplication time, I'm sure many of you know this term. So pick your favorite algorithm for multiplying two n by n matrices and let TMM of n be the number of bit operations that algorithm takes. Then this result is saying that you can solve this problem in this number of bit operations using only polylog n over delta bits of precision. So using state-of-the-art matrix multiplication algorithms, for example, you get this dependence in the number of bit operations. And as you can see, this is even an improvement in the Hermitian case. Okay, so let me tell you what are the main ingredients for a proof. So first, there's some contribution that can be thought of as a purely random matrix result. And the thing is that we exploited the fact that randomly perturbed matrices have stable eigenvalues and eigenvectors. So in the spirit of smoothed analysis, this is used as follows in our analysis. So given some algorithm I that you're going to use to solve the approximate diagonalization problem, instead of running it on the matrix you're interested in, first perturb the entries of the matrix by tiny random noise. So that's going to be A tilde, and then run your algorithm in A tilde. So this is a fundamental step in our analysis, and we show that this preconditioner by adding random noise is actually very effective. And our second contribution can be thought of as an algorithm analysis contribution. So we proved that Roberts-Newton iteration for computing the sine function is numerically stable globally convergent, and one can do it efficiently. So to give you some context, this is the first proof that the sign function can be computed efficiently in a stable way for arbitrary matrices. And the thing is that many numerical linear algebra algorithms rely on being able to compute the sign function. So in particular, the algorithm for computing eigenvalues and eigenvectors that we analyzed is the spectral bisection algorithm, which was introduced by Beavers and Denman in '74. And it wasn't known if this algorithm was globally convergent and numerically stable. And the bottleneck precisely was to show that the sign function can be computed in a stable way efficiently. Okay, so now for the last part of the talk, I'll give you a bit of details for both contribution 1 and contribution 2. Okay, so first about this random matrix fact, let me be more precise. So take an n by n random matrix where the entries are independent, complex, standard Gaussian random variables. And you can think of A as the matrix you're going to diagonalize. A tilde is a random perturbation of A, where you're adding Gaussians to the entries of A with tiny variance. So Banks, Kulkarni, Mukherjee, and Srivastava in 2018 showed that the eigenvalues of A tilde are stable, and they're stable in the following precise sense. For any small matrix E with norm less or equal to epsilon, the eigenvalues of A tilde plus E get displaced from those of the eigenvalues of A tilde by at most this quantity. So it's epsilon, and it's a multiple of epsilon, and the multiple has a polynomial dependence in n and delta inverse. And later in the paper that I'm presenting right now, we built on this result to show that the eigenvectors of A tilde are also stable in the same sense. And these two polynomials are quite tame. Okay, so that was the probabilistic contribution. Regarding the computation of the sign function, first let me define what the sign function is. So the sign function of a matrix A is a matrix with the same set of eigenvectors, but the eigenvalues are either 1 or -1. And to be more precise, you put a 1 for every eigenvalue that's on the right side of the complex plane, and you put a -1 for every eigenvalue of A that is on the left side of the complex plane. And so let me put that equation there as a reminder. The Newton iteration that Roberts introduced is as follows. So you create a sequence starting at A, and then AK is going to be the average of the previous term plus its inverse. Okay, so it is not hard to show in exact arithmetic that this sequence converges to the sign function of A. So for example, here are the eigenvalues of a matrix, so of a matrix A. This is the complex plane. These stars are 1 and -1, and this line is the imaginary axis. So as you see, as the Newton iteration evolves, these 1 and -1 are attractors, and each eigenvalue goes to the side it should go. And moreover, at every step, the eigenvectors of AK are equal to the eigenvectors of AK -1 in exact arithmetic, right? So that gives you an idea on why this is true. But the real complication in finite arithmetic is that an error is introduced at every step. And hence, it's no longer true that the eigenvectors of all the AKs are the same, right? And moreover, the conditioning of the AKs might worsen at every step because of this error, and leading you to the conditioning like eventually blowing up, or maybe leading you to having some AK with very unstable eigenvalues such that one of them jumps from the right side to the left side of the complex plane. And you get, of course, an inaccurate output if this happens. So to conclude the talk, let me tell you explicitly what we proved. We showed that the approximate side function can be computed in a numerically stable way in nearly matrix multiplication time. And precisely the algorithm that this theorem is referring to is Roberts' Newton iteration. And just one last thing. So there are some technical terms that I avoided defining in this short talk, but that are crucial for our analysis. And I refer you to the long talk for the definition of these terms and for how they're relevant in our proofs.
Thanks, Jorge. Very cool. Questions? Salil has a question. Feel free to unmute.
Hi, thanks for the talk. Can you repeat what the improvement you mentioned you get in the Hermitian case is compared to what was known before?
Yeah, before it was known to be n cubed, so maybe I should go back to it. And we got nearly matrix multiplication time. So given that it is known that one can multiply, so this is the Hermitian case. And here is what we got. So it's known that this you can make smaller than n cubed. Some conjecture that the matrix multiplication exponent is n squared. So if you get a better matrix multiplication algorithm, you'll improve over this.
Thanks.
Chandra asks, why is it nearly matrix multiplication? Do you mean polylog factors?
Yes. So precisely, there's here. Yeah. So essentially, the proof is showing that you can diagonalize using only polylog manifolds to matrix multiplication. That's what this is doing. And here the C, I think it might be a 7. Yeah, I don't quite recall.
Manuel asks, have you implemented this algorithm? And if so, how does it perform in practice? Is only order n squared polylog memory needed?
Okay, so about the implementation, there's, yeah, this algorithm is widely used. So maybe I should go to this slide. So this was introduced in '74 actually, and people have used it extensively. I kind of forgot where I put it, but anyway, oh, okay, here it's Beavers and Denman from '74. And there's optimizations that have been done regarding the memory and the minimizing communication and so on. About how many memory it uses, I'm not quite sure actually. What was the question? N squared log n?
Right. Yeah. Is order n squared polylog memory needed, or do you need more?
So this is a recursive algorithm. So essentially, you get like the eigenspace corresponding to the right side of the complex plane and the eigenspace corresponding to the left side, and then you deflate the matrix. So you just have to store what you get in each deflation, and every time you multiply what you get, so it doesn't add kind of like extra memory. So I think that's correct, but yeah, I'm not completely sure about that.
More questions? Okay, if not, we can switch to the next talk. So next we have Algorithms and Hardness for Linear Algebra and Geometric Graphs by Josh Allman, Timothy Chu, Aaron Schild, and Zhao Tong. And I'm not sure who's giving a talk.
So I'll be giving the talk. I'm Timothy Chu.
Go for it.
Great.
Feel free to share screen.
Okay.
You're visible.
Can you hear me?
Yes.
Great. And you can see the screen and everything.
Yep.
Great. Cool. So my name is Tim, and I'm presenting on Algorithms and Hardness for Linear Algebra on Geometric Graphs. This is joint work from Josh Allman, Aaron Schild, and Zhao Tong, whose affiliations you can see on the slide. So I'll give a brief roadmap for this presentation. What problem are we solving? These are the questions to keep in mind. Why are we solving it? And what are some notable results in our work? We'll be going through these 3 points in order. So the problem we're trying to solve is fast algorithms on geometric graphs. Okay, what does that mean? Well, we're going to consider a class of geometric graphs, which are going to be complete graphs from n points in d dimensions. And we're going to try to find fast algorithms on these for a set of algorithms we'll define later. So these algorithms, sorry, these graphs, because they're complete graphs, have n squared edges. However, their input size is n times d. So if d is noticeably less than n, you can actually hope for subquadratic time algorithms, depending on what problem you're trying to solve. So before we dive into all the details, let's first restrict ourselves to a special class of these graphs called k-graphs. And this restriction is not actually that restrictive. So what is a k-graph? It is going to be defined as follows. Basically, what you're going to do is you're going to take n points in your d-dimensional Euclidean space, and you're just going to draw the complete graph of all n nodes. And you're going to define the edge weight between node I and j to be k applied to xi, comma, xj. And in our talk, we're going to restrict our attention to functions k, where it's a function of the Euclidean distance. So that went a little quickly, so just to summarize, we're trying to find fast algorithms on k-graphs, where k-graphs are defined by taking a complete graph on n points in d dimensions, and setting the edge weight to be a function of the Euclidean distance of their endpoints. So we're going to go through a couple examples in case that was still too fast. So let's consider the case where k of x and y is just the Euclidean distance. Now, the k-graph of x1 through xn is a complete graph of n vertices whose edge lengths are the Euclidean distance between points. So it's pretty simple. I've shown such a k-graph when n is 4. And the edge lengths in this complete graph are exactly the edge lengths you see. And in general, you could use any function of the Euclidean distance, and the k-graph would be the complete graph on n vertices, whose edge lengths are that function applied to the squared Euclidean distance between the points. Great. So that's our definition of a k-graph, and that's the kind of geometric graph that we're referring to throughout the course of this talk. Now, I promised fast algorithms, well, and hardness results for geometric graphs. So let's turn our attention to what algorithms we want to be considering. So we are going to consider the following 3 problems. The first of which is the matrix multiplication, vector multiplication problem. When you have a graph, often you have a matrix associated with this graph called the adjacency matrix. And in some settings, you may prefer to use a different matrix called the Laplacian matrix. The question is, can you multiply this k-graph's adjacency or Laplacian matrix by any n-dimensional vector? Now, of course, you can do this in n squared time, just by doing it. But our whole talk is about whether you can do faster than that. The second question we will address is whether you can find a spectral sparsifier of your k-graph. Now, for those of you less familiar with spectral theory, a spectral sparsifier is simply a sparse graph that approximates some of the properties of our original graph. And it's not too important what this definition is. The key is, can you find a sparse graph that closely approximates some properties of our k-graph? And the final question is the Laplacian system solver question. That is, can you approximate x such that Lx equals b for a given b? Here, L is the Laplacian of the k-graph. So these 3 questions are pretty standard fare in spectral graph algorithms or linear algebra on graphs. Now, the only trick, though, is we want to solve these problems in, faster than quadratic time. Of course, you could solve all these in roughly quadratic time just by writing out your entire k-graph and using existing algorithms. But because we have n points in d dimensions, hypothetically speaking, we could possibly do n times d time if d is much smaller than n. So the question is, can you solve these faster than the naive quadratic algorithm? In particular, can you solve these in almost a linear time, aka n to the power of 1 plus little o of 1, in the case where d is O of log n? This includes both the high dimensional case when d is, say, 100 log n, and also the low dimensional case when d is, say, 2. And of course, there is going to be some dependence on the approximation factor, like we're only solving our 3 problems up to an approximate factor, but we're going to omit that approximation factor during this talk. And if you're really interested in that, you can see the rest of our paper. So let me briefly get into the second key point of this talk, which is why we want to solve these questions. And the 3 questions are matrix vector multiplication, when the matrix comes from the K-graph, spectral sparsifiers of the K-graph, and solving a Laplacian system where the Laplacian matrix is generated from our K-graph. Well, these 3 problems are fundamental linear algebra questions. These are probably the most basic questions you could ask within linear algebra on graphs or spectral graph theory. Moreover, geometric graphs are quite common in computer science. They appear in all sorts of fields, ranging from computational geometry, machine learning in a variety of settings, image recognition, physics simulations, so to say, tracking the orbit of a bunch of planets, and more. So it actually seems quite natural to try and find fast algorithms and hardness results for fundamental linear algebra problems on a set of graphs that appear everywhere in computer science. So our motivation here is sort of from an academic point of view. You know, there are common linear algebra questions and there are common geometric graphs. So why not try to solve these linear algebra questions on these geometric graphs? But for a more concrete motivation, our results actually give you interesting insight into a wide class of algorithms on geometric graphs. For example, there's an algorithm known as the fast multipole method. Now, if you don't know what this is, it's not too important for this talk. But the key idea is this algorithm is a way to quickly find out the gravitational force on a planet. So imagine you have n planets in d-dimensional space. Each planet exerts a gravitational force on each other planet. How can you quickly compute for every planet how much gravitational force is being exerted on it? The fast multipole method is a quick way to do this that's very popular in physics simulations. However, it has an exponential dependence on d. Usually, when you're thinking about this problem, it's in 3 dimensions, so it's fine. But the question is, do you need this exponential dependence on your dimension d for solving this planets and gravitational forces problem? And our work shows actually, yes. Yes, you do. So not only is our work interesting or not only were we motivated by our work for these theoretical reasons, but we actually proved new results about long-standing algorithms like the fast multipole method. Again, if you don't know exactly what it is, it's not too important. It's just a famous algorithm from the 80s. We should also note that our work has applications to spectral clustering, solving maximum flow in nearly linear time on geometric graphs, semi-supervised learning, and more. And for a complete list of the applications our work has, you can see the introduction of our paper. So we went through what problem we're trying to solve, fast algorithms or hardness results on geometric graphs. We went through why we want to solve it, theoretically interesting, and it has applications to other algorithms. And now we'll just briefly cover some notable results in our work. So the basic idea of our work is we want to know for which k and which dimensions d can we find close to linear running times, and for which k and which d can you not do better than quadratic running time, right? So algorithms and hardness. And here are 2 of our results. We have an algorithmic result and a hardness result. So the first result says, for any function f that is a polynomial with positive coefficients, the associated k-graph has a spectral sparsifier you can find in close to linear time in n. This also works if f is any rational function of the Euclidean distance, as long as all the coefficients are positive. Again, this may be surprising because the graph itself has quadratically many edges. The second notable result we'll go through is that both matrix vector multiplication and solving Laplacian systems must take close to quadratic time if you're in roughly log n dimension. And this is for any function k that is not tightly approximated by a polynomial. And we're going to assume some complexity hypothesis here. If k is approximated by a polynomial, you can do these quickly. And here are a couple examples of functions that are not approximated by a polynomial. So for these functions, you cannot do matrix vector multiplication in faster than quadratic time, assuming you're in high dimension. Now I know I'm almost out of time, so I'll briefly, I'm going to skip the way that we do these. But at a high level, we're addressing these three problems of interest, and we're finding both surprising algorithmic results when you can do these quickly, and also hardness results for when you can't. And for a more complete classification of the K and D for which these problems are either hard or have fast algorithms, refer to our full paper. And we don't have a complete classification, but we actually have something pretty close to a complete classification. So for all three problems, and for a large suite of dimensions D, our paper tells you whether the problem is hard, aka takes roughly quadratic time, or whether it's easy, aka takes roughly linear time. Thank you very much. And I believe that's my 10 minutes for the short talk. Any questions?
Yeah. All right, so we have a couple already, and feel free to line up more in the chat or raise hands. So Arsen asks, do we assume access to Oracle that computes K?
Yes, K is assumed to be computable quickly.
All right, that was short. Then Samson asks, does tightly approximated by polynomial refer to some kind of Taylor series expansion?
Kind of. The short answer is, sorry. Yes, but it's a little complicated. So the full formal definition is in our full paper, but it doesn't hurt to think of it as like a Taylor series thing. Like basically all the Taylor series beyond a certain point, or all the Taylor coefficients beyond a certain point, let's say, are super, super small. There's a real formal definition in our paper, but it doesn't hurt to think about it in terms of this Taylor expansion. Any other questions?
Salil has his hand up.
Maybe I misunderstood what you said, but it sounded like you said that the positive result you have, the fast algorithm, applies even if the function is a rational function of the distance.
Yes.
But then in your negative result, you mentioned that this case of the 1 over the squared distance is a hard instance. So I was just having trouble reconciling the two. Could you elaborate?
So one of them, they're for different problems. The rational function thing I mentioned was for the spectral sparsifier problem. And the hardness result is for a matrix vector multiplication problem. So
I see. I see.
Different problems, different regimes. It was I apologize for the lack of clarity there. But yes, easy for spectral sparsifiers, hard for matrix vector multiplication.
I see, but then once you sparsify, you can't then just apply for like solving Laplacian systems. You can't just work with a sparsifier.
That's a great question. There's a little technicality here, which, as you know, I hid the epsilon term. And the key here is that normally when you talk about solving Laplacian systems, usually your dependence on epsilon is like log 1 over epsilon. And what that means is you want to solve Laplacian systems to very high precision. But for spectral sparsifiers, generally you're okay solving it to low precision. So basically what you say is correct, but I sort of hid the technicality around approximation. So what this result really says is finding low, like coarse approximations for spectral sparsifiers is doable for rational functions, but finding very fine approximations of Laplacian systems is hard for rational functions. And the reason we have coarse for spectral and fine for Laplacian systems is this is what the existing literature does. So in short, you're correct that you could sparsify first and solve the Laplacian system, but I'm secretly like addressing it for different approximation regimes. Does that make sense? Sorry if that was a...
Yeah, yes, it makes sense, but maybe I'm still a little confused. So you can't then use the spectral sparsifier as a preconditioner?
Oh, I see. You want to like precondition it. Okay, I see.
We can also discuss offline.
Yeah, this sounds like a great candidate to maybe take offline, I guess.
I can say this actually briefly. The problem with preconditioning is I think it takes roughly O of m time, but here m is like n squared. Like if you actually try to do the preconditioning step, it will take roughly the number of edges in k time to even do.
Great. Thank you. That clarifies. Thank you.
Great. Any last questions? I've got like 1 minute left.
Yeah, maybe let's try to fit in one more. So David Wu asks, how fundamental is the assumption that k is a function of the Euclidean distance for the proof techniques?
We can solve this for other settings. In fact, we do. For example, when when k is like a function of the dot product between x and y, we also have another suite of results. But basically, a lot of our techniques don't quite work for other functions at k. So basically, it is fairly essential to the proof. These functions are common in the literature, but it is an open question that we would love to see resolved. For what other kinds of functions k can you solve these or find hardness results for these algorithms? Does that answer your question?
Yeah, I'm gonna assume yes. So, all right, there's a couple more questions lined up, but maybe you can take it offline or on Slack, so we keep to schedule.
Right.
Thanks so much. Yeah. So the next up, we have sparse PCA algorithms, adversarial perturbations and certificates by Tommaso, Pravesh, Gleb Novikov, and David Steuer, and Tommaso is giving the talk.
Sorry, how do I stop sharing?
Oh, where you have share screen, there should be stop sharing.
Hang on. Sorry about this. I can't find the button. I'm sorry. Is there a way you can cut my feed?
It's a good question, Tommaso. If you try
Just
sharing,
leave the session.
I'll try.
All right, I'll leave the session and come back.
that works too.
Okay. So let me share a screen. Okay, so you can see my screen, I assume.
Yes.
Okay,
Visible and audible.
Thanks for the introduction. So here we talk about sparse PCA, algorithms, adversarial perturbations, and certificates. As you said, this is a joint work with Pravesh Kothari, Gleb Novikov, and David Steuer. So let me start just by briefly recalling what sparse PCA is. So we have n samples in d dimensions in some matrix Y, and these are noisy samples. So here W is a Gaussian matrix. And our goal is to find some, to recover some signal V0. And this signal has some structure. In this case, it is sparsity. So we're fine with obtaining an approximate version of V0. And just for the sake of the talk, let me assume that the signal strength is larger than 1. So just to simplify the bounds that we're going to see. Okay, so if we try to solve this algorithm, we disregard computational efficiency, then, I mean, simple approach is exhaustive search, and we try to maximize the sparse quadratic form of Y. So this approach works very well in the sense that we need the signal to be larger than k over n. K here is the sparsity. And let me just say that I wrote much larger than k over n to avoid logarithmic terms. There are many interesting questions about them, and you also find results about them in this paper. So I don't want to have time to discuss those. So this is optimal, but of course it's inefficient, brute force, and it's exponential in k. So if we try to instead use efficient algorithms, then we can divide the literature into regimes. The strong signal regime, where beta is larger than square root d over n, and the weak signal regime. So in the strong signal case, what happens is that the principal component of the empirical covariance is correlated with the signal. And so this is, I wrote correlated in quotes because you might need some additional step in the sense that the principal component may not be correlated, but after some simple thresholding, it's correlated. You get a vector that is correlated. So some kind of like singular value composition, some simple spectral algorithm works. And the guarantees that we get in this case are essentially the same as the brute force algorithm. So in the weak signal regime, instead, things are a bit different. There's a gap between what we can do efficiently and what we can do statistically. So we need to assume that beta is larger than k over root n. So there's a root n gap. And so the algorithms we have are diagonal thresholding and semi-definite relaxation or sum of squares. So here, if you don't know diagonal thresholding, just think of it as applying some thresholding step and then some spectral algorithms. That is fine for talk. Okay, so with this picture in mind, I want to introduce the problem that we consider, which is a modification of sparse PCA, in which there's also an adversarial matrix E. So this E can depend on essentially all the information that we have. So V0, U, and the noise, etc. And the goal is still to find just an approximate vector close to V0, an approximation of V0. So of course, so usually we think of adversarial perturbations as I don't know, introducing some kind of outliers. Here we use a different definition in which E can be a dense matrix, but entries have to be bound. So it turns out that this kind of bound has to be done a little bit carefully. So if the entries are too large, then trivially we could remove the signal, and then the problem is not interesting. And similarly, if the entries are too small, then essentially we're just doing a sparse PCA, so there's nothing to say. So it turns out that the right choice is to bound the entries of E in absolute value by square root of beta over k. And the reason for this is that as long as this bound holds, then V0 is non-trivially correlated with the sparse quadratic form of Y. So what I'm saying is that essentially, as long as this bound holds, then the exhaustive search algorithm has the same guarantees for this robust version of the problem. Okay, so let's go back to our picture of efficient algorithms, and let's consider this robust version of the problem. Then what happens is that some algorithms still work in this robust version, but the spectral algorithms fail. So in particular, diagonal thresholding and single variable composition can be fooled by these adversarial perturbations if we choose them carefully enough. So I guess this naturally prompts the question of why some algorithms succeed and why other fails in the presence of these perturbations. Okay, so let me try to give you some motivation for this. So we say that sum of squares and, I don't know, semi-definite relaxation are certification algorithms in the following sense. So suppose we have some maximization problem, and it shows maximization of a sparse quadratic form over a Gaussian matrix. So this is closely related to our problem, that is the reason. Then, I mean, the certification version is somewhat, we try to provide some bound, some omega that is larger than the sparse quadratic form. And I mean, a very common approach to this is our convex relaxations, of course. So we have some constraints and we relax the constraints, and that's how we get this certification algorithms. So in our case, concretely, what happens is that the quality of the algorithms that we get depends on the sparse, the bounds that we can certify on the sparse quadratic forms of the noise matrices W. But in any case, I guess I wanted to say this to introduce the moral theme of the paper, which is that algorithms that comes with certificates of sparse quadratic forms are robust, in the sense that they can solve the robust version of the problem. And algorithms that do not produce these certificates, such as the spectral algorithms, they can be fooled by these arbitrary perturbations. And I put a star here in the sense that this is not a statement that we are proving, but rather like the moral theme of the moral belief that we have. And so, I mean, this is something that's been observed already in other works, maybe not in this explicit version, but still we have seen these things multiple times, also in this conference. So this provides some difference between sum of squares and spectral algorithms in a qualitative terms. So concretely, the result that we have is that sum of squares can solve the robust sparse PCA problem. And so the bounds that we have are in the weak signal regime, then we constant degree of the hierarchy and standard SDP relaxation, they work as we said already, similarly as in the project setting. So up to constant factors, the guarantees that we get are the same. In the strong signal regimes, things are different. So we get the algorithms require a higher degree of the sum square hierarchy. So in some sense, we require algorithms that are computationally more expensive, and the bounds that we get are not as good as before. If you don't remember the ones I showed you, just see that the bounds on beta looks more complicated, and we have another constraint that relates D with N. So here we require D to be larger than N to the T, where T is the degree of the sum square. So what is happening is that for the surround singular regime, we don't get the same guarantees as in the project settings, and in particular, these are worse than what we used to take. So, I mean, the natural question is now, why cannot we do better? Is there some kind of evidence that shows that there's a price to pay for robustness? And so what we show is that we provide formal evidence in the sense we provide a lower bound for low degree polynomials. So this essentially shows that the bound on beta and D for the strong signal regimes are tight. You need polynomials of exponential degree to overcome those bounds. So this implies some inherent statistical gap between what we can do in the fragile settings and what we can do in the robust settings. So as I said, this is some kind of evidence for a price to pay in order to get a robust algorithm. Okay, so I guess this was the main result that I wanted to show. I want to use my last minute and something for the other results that we have in the paper. So in particular, we show the novel analysis of the basic SDP, and the result is that now it matches the guarantees of all previously known polynomial time algorithms in the weak signal regime. And this is so applies, of course, in both the fragile and robust settings. The other thing is that there are sub-exponential algorithms for sparse PCA in the weak signal regime, and they are not robust. So what we also get sub-exponential robust algorithms. As I mentioned at the very beginning, there are some interesting questions about logarithmic factors. And so essentially, with our insight of the lower bound, we get some nice algorithms based on polynomials that and some sharper lower bounds that allow us to somewhat close the gap that was there before. So what happens now is that in most regimes, algorithms and lower bounds match up to constant factors. And finally, I want to say that, I mean, one of the drawbacks of SUM of squares is that it's hard to run in practice. And so we provide a fast spectral algorithm that simulates a robust SUM of square algorithm up to degree 6. And so this is, of course, not robust, but it's robust to against the adversarial matrices that we use to provide the lower, to prove the lower bound. And it is a strengthening of an algorithm that I think appeared here at Stock a few years ago for the plan to sparse vectors in a random subspace. So this is all I wanted to say. So thanks a lot, and we're open to questions, and Gleb is here also to help me answer.
Thanks, Tommaso. Questions for Tommaso? I can kick it off, I guess. So I guess it's always a little bit hard in SUM of squares kind of talks, but could you see a little bit at the level of techniques, I guess, there's something new or interesting?
Right, so I think for the bounds that we get, at least for the one that we described here, I should have some course on SUM of square. Yes, so I guess so we use for the strong signal regime, we use some techniques that were already that are not new in the sense that we use certifiable sub-Gaussianity. So in particular, we want to certify some bound on the sparse quadratic form of the Gaussian matrix. And so it depends on the regime, but let's say in weak signal regime, maybe you can use some simple spectral bound, and in the other case, you need to use certifiable sub-Gaussianity, and that's how you get this also, these constraints between the ds to be larger than n to the t. For the sub-exponential algorithm, you need some I guess new ideas, but still this comes from, you look at the sub-exponential algorithm that you know, and you try to SUM of squareize them in some way. I guess that's the approach.
I guess there's a related question by Ainesh. Can you say a bit more about the constraints you use in your SUM of squares relaxation? Are there any new ones?
Yes. No, that's okay. So this is the SUM of square relaxation that we use for the polynomial time algorithms, and actually for both the fragile and the robust case, and for the sub-exponential algorithm, you need a couple of constraints more. Yeah, this is the main sum square system of inequalities that you use. So you're still seeing my screen, and so you see the slide.
Yeah, your screen was visible just fine. Yeah. Cool. Thanks, Tommaso. So I guess we have the last talk of the session. So we have maximizing determinants under matroid constraints like Vivek Madan, Sasha Nikolov, Mohit Singh, and Utaipon Tantipong Pipat. And I think Mohit is giving the talk.
Yes, thanks, Andre. Let me try to share my screen. Can you see my screen and hear me?
Yes, you're good.
Okay. Thanks everyone, and thanks for sticking around for the last talk of the session. I'm going to talk about maximizing determinant under combinatorial constraints, and in particular matroid constraints. This is joint work with Sasha Nikolov, I believe, who's also in the chat. Vivek Madan, who recently moved from Georgia Tech to Amazon, and Tao, who also recently moved from Georgia Tech to Twitter. So let me directly define you the problem. It's a slightly abstract problem, but it's just good to see the definition first. So I'm going to give you n vectors in RD. Think of n as really big and d as small. And also I'm going to give you some combinatorial set family. And what the goal is to pick one set from this set family, so some subset of the vectors, to maximize the determinant of the sum of the rank 1 outer products of these vectors. So summation over I and S, where S is a set you picked, VI transpose. You want to maximize the determinant of this. Okay, and I'll be talking about multiple sets of different set families. We'll formalize that more. While the problem looks very abstract, actually it surprisingly captures many well-studied problems in a diverse set of areas, like in statistics, machine learning, network design, even problems in fair allocation. Of course, it also naturally captures problems in convex geometry as well. More interestingly, it also gives a general framework to study many of these problems. And in many of these settings, the best algorithms are actually possible just via this general framework as well. Okay, so before I tell you what we do about this problem, let me briefly talk about a couple of applications as well to give you some intuition. So the first application actually comes from the area of statistics, classical statistics of experimental design. So in this problem, we are given some unknown theta star that we want to know. It's in d dimensions. What you can only do is do linear measurements of this theta star. So you can take a vector vi, take its inner product with theta star, but every time you do such a measurement, you also get a Gaussian noise added to it. So you observe yi over here. Okay, so you observe this yi every time you do. And you can do these measurements, but unfortunately, you cannot do all the measurements because that's too costly. You can maybe do only k measurements, or for example, you could have more combinatorial constraints on the set of measurements you can do. And the goal is to pick which measurements to do so that you actually can estimate your theta star as well as possible. Now, of course, once you've done the measurements, the most likelihood estimator is quite easy to calculate, and that's usually done by a least square calculation. Now, once the error actually turns out under these noise assumptions is also error vector, how much error you have, also behaves like a multivariate Gaussian. And you can look at the confidence ellipsoid of it, which is basically how, like, with what confidence you are sure with a constant probability, for example, where the true answer is set. And you can ask to make sure this confidence ellipsoid is as small as possible. And one measure of that is what is called a d-optimal design problem, which minimizes the volume of this confidence ellipsoid. And it turns out this problem is exactly equivalent to the maximizing determinant problem that I just told you. Okay, and there's been a series of works, classical from in statistics, and giving very nice algorithms and simple combinatorial algorithms as well. It turns out for cardinality constraint is where it has been studied the most, and what we're going to look at much more richer combinatorial constraints. Okay. Let me also talk about one more application from a very different area of network design. So in the network design, typically we are given some graph, and our goal is to find some spanning subgraph. So not pick all the edges, but some subset of the edges, such that we want the subgraph to be well connected. And moreover, we want to make sure we don't pick too many edges. For example, we have maybe some cardinality constraint on the set of edges that you pick. You pick no more than k edges. Now, of course, I haven't told you what the definition of well-connectedness is. There have been many definitions that have been studied. One of them, which was recently proposed, was also to say that I will call my graph well-connected if it has lots of spanning trees. So our goal is to maximize the number of spanning trees in this graph. It turns out this is also a special case of our problem, determinant maximization problem, and that's basically follows from the Kirchhoff formula as well, right? Trying to find a well-connected subgraph where well-connected then means maximizing number of spanning trees. So these are two simple applications of the more abstract problem. So let me formalize the problem for you again. So I'm giving you n vectors in RD, and our goal is to maximize, pick a subset and a set family that we're given. The set family we'll consider is the basis of a matroid of rank K, which will be going to be bigger than D. And our goal is to pick one basis and to maximize the determinant of the sum of rank 1 matrices formed via transpose for all the vectors in this basis. For appropriate scaling purposes, because this determinant is a D by D determinant, so I will scale it to the dth root. So that's appropriate scaling to do. So just if you haven't seen matroids before, it's just some simple examples. Uniform matroid is a very simple matroid where the set of bases are any set of size k. A bit more richer matroid is a partition matroid where I, for example, give you a partition of my ground set, and I tell you from each part how many elements to pick. For example, in this, from the first 4 vectors, I tell you pick 1 vector. From the next 3, pick 1, and for the next 3, pick 2. And of course, you have a choice which one to pick and so on. You could have much more richer matroids as well. For example, the set of spanning trees of a graph also form a matroid. And so on. Okay, good. So that's the problem that we will be studying. So let me state our results. So our first result is that we give an order D estimation algorithm for this problem. So we can give a polynomial algorithm which estimates the value of this the objective within a factor of order D. Remember, D was the dimension for any matroid of rank K. From an algorithm perspective, which returns a solution, we give a deterministic polynomial algorithm which returns a solution which is within a factor of order D square, so which is slightly worse than the estimation algorithm. And it's actually a standard issue with almost all algorithms for determinant maximization problems that have been studied. The estimation algorithms are much easier to obtain than obtaining the real solution in polynomial time. Okay. Good. So let me briefly tell about the previous work just to put our results in context. There's been a lot of work on uniform matroids, and a constant factor approximations are known for uniform matroid. They're also known for partition matroids and more general matroids as well, as long as the rank of the matroid, which is the size of the set you're picking, is same as the dimension of the vectors. You can also apply all of these techniques for the larger rank. Unfortunately, then the approximation factor grows exponentially in the size of the set that you're picking. Okay, all of these techniques generalize. So our goal, our main contribution is to improve these approximation algorithms and give something which is independent of K, only depends on the dimension. From a technique perspective, all of the previous results rely on properties of stable polynomials and more recently introduced notion of strongly log concave polynomials. Our results also use these results very crucially. But in particular, we also introduce give a new structural result that natural convex relaxation for this problem actually has sparse optimal solutions. Okay, and this, and I'll briefly talk about this. This is the only technical part I'll talk about in the next 2-3 minutes, and it relies basically between interplay of first-order conditions of convex programs and matroid theory. Okay? So let me go into this technical thing. So let me, for that, tell you what the relaxation is. So the first natural relaxation you can try to construct is to introduce decision variables for each vector, whether I pick it or not, and then you can write your objective as just maximizing the determinant of summation xi via ui transpose, where you sum over all vectors, and you insist that the x vector lies in the convex hull of all feasible sets. It turns out the nice thing is it actually gives a good approximation for uniform matroids, and it also has some nice sparsity properties. But unfortunately, it doesn't work for general matroids. Actually, it only works for uniform matroids. Even for very special partition matroids, it cannot detect whether the answer is 0 or non-zero. Actually, that's a nice puzzle where detecting the answer is 0 or non-zero. You can actually do that in polynomial time using matroid intersection. Okay, so now the challenge is how do I get a better relaxation? And the trick to do that is to first apply Cauchy-Binet formula to the objective and write the objective as a polynomial. It's a degree D polynomial because it's a determinant of a D by D matrix. And you get basically terms over here, monomial terms for every subset of size D. And what you really want to do is only to sum over sets over in the subset R, which are some subset of some independent set. So I don't want to sum over all subsets, but only over independent sets. Unfortunately, doing that directly will not give you a convex program. It might not be even computable. So the trick to do is to use a trick from matrix scaling. What you do is introduce a new variables y, which are used to scale your vectors. And you insist that for every, introduce polynomial constraints on y variables, such that for every monomial term that you wanted to count, which are the independent sets of size d, the monomial term is evaluates to at least 1, and you minimize over all such scalings. Okay, now it can be written as a convex program and solved efficiently. It's also related to a very well-studied convex program. What we want to show is actually some sparsity property. Let me briefly tell you what that is. It turns out actually you cannot directly round this the solution to this, and we actually show if you just directly round this convex program, you will fail to achieve any approximation which only depends on the dimension. Okay, which is also done in all previous works. So the structure result is actually to show that this relaxation has one optimal solution which only has order d square fraction variables. And the way to do that is we write down the first order optimality conditions. Unfortunately, the first order optimality conditions are non-linear and they're exponentially many. And how do we get rid of these? So the main idea is to introduce additional linear constraints to avoid these non-linearity. And we also then use matroid theory, in particular uncrossing methods, to deal with exponential number of these constraints and still argue that they are only order d square fraction variables. One last line about the rounding algorithm. One has to be still careful, even though we know most of the variables will be set to integer value, you cannot pick all the variables which are set to 1 because the objective is actually a polynomial of degree d, not a linear objective function. Okay. So just to recap the results, we give an order d estimation algorithm and an order d square rounding algorithm, which returns a solution in deterministic polynomial time. Just to end, a couple of open questions. One is that, of course, naturally is we give an order d approximation for estimation. Can you improve it to order 1? And it's known for partition constraints, but not for general matroid constraints. I only talked about the determinant. There much less is known for objectives apart from determinant. In some sense, for example, you could try to maximize the minimum eigenvalue, which is also captures many different problems in many different areas. Okay, let me end there. Thank you.
Thanks, Mahit. Any questions for Mahit?
So Mohit, I have a question. So yes, the problem wouldn't make sense to look at matroid intersection constraints because you can't even check if the optimum is 0.
So you could try to write some matroid intersection constraints, but a priori it's not clear. That's the objective is a polynomial. So like just insisting you can write down linear matroid intersection constraints as well, but it turns out.
No, as you pointed out, checking 0 already seems like 3 matroid intersection.
No, checking is 0 is actually 2 matroids.
Even with matroid intersection constraints?
Not with matroid. Sorry, yeah. You mean if you had matroid intersection constraints? Yes, then you cannot detect the answer is 0 versus non-zero.
So it doesn't make sense to think about this problem for matroid intersection constraints.
Yeah, unless you relax it somehow. Yes. Look at bicriteria, for example.
Thank you.
More questions?
Mohit is Chandra. Any other matroids for which you can get constant factor other than partition matroids?
No, basically as long as the matroid, like the rank is small as compared to the dimension, like as I mentioned, like yeah, so this result of an RE-Oveshkiran invention gives a E square for matroid as long as the rank is D. But when the rank is bigger, basically you will only get either e to the 2k over d kind of approximation, or what we have is order d.
I'm just wondering, the natural generalization of partition to laminar with, say, some depth or something.
Possibly, like we didn't think too hard on it, but I would guess at least for constant depth laminar matroids, yes, those kind of things will be possible. But I think if I would directly, I would claim, hope that what we show, for example, is that the sparsity result over here, instead of order d squared, should be actually order d. This should be order d. And then if it were order d, it would imply a constant factor approximation.
So I mean, the D's are different, but that's what you mean, yeah.
Like the optimal solution will have only order d fraction variables. That's what we conjecture. We can only prove order d squared.
Oh, I see. So you're saying even for general, if it is d, you're saying you'll get a constant factor.
Correct. Exactly.
Ah, okay. Thank you.
But we don't and that's what we conjecture, but we don't know how to prove.
Thanks.
And maybe if this has a short answer, Michal asks, how do you perform the rounding to obtain the order d squared solution from the relaxation?
So yes, so that has to be like carefully done using so for example, most of the variables are 1, like except for d squared. The variables which are set to 0, those you can completely ignore. Basically, all the variables which are set to 1, you pick them with probability half, as long as you maintain a feasible independent set. And then all the fraction variables you pick with the probability like 1 over d as well, of 1 by 1. So you just make sure you give priority to the elements which are set to fraction value 1, but you want to make sure you don't pick all of them. You leave some gap for the fraction variables.
Great. Thanks, Mohit, and thanks to the speakers as well as the attendees, and see you all around. That concludes the session.